Hello method students. In this video we're going to be having a look at types of stationary points and how we can use the gradient of a function to determine what type of stationary point we've got. So we've already seen that at a stationary point the gradient is 0, right? That's the definition of a stationary point. But if we investigate what's happening just before and just after a stationary point, we can work out what type of stationary point it is. For example, if the gradient is positive before a stationary point and negative after it, then we have a local maximum, because it's like we've got positive gradient, then 0 gradient, and then negative gradient. So that must be a maximum turning point. Similarly, but the other way around, if the gradient is negative before a stationary point and positive afterwards, we have a local minimum, because that's like negative gradient, 0 gradient, then positive gradient. If the gradient is the same side either side of a stationary point, then same sign either side of a stationary point, then we have a stationary point of inflection. So if you had, say, positive gradient, then 0 gradient, then positive again, that's going to be a stationary point of inflection. Likewise, if it was negative, then 0, then negative, that would also be a stationary point of inflection. So we can kind of use that if we're trying to generate a sketch of a graph and work out what sort of stationary point we're going to be looking at, again, assuming that we're not able to use our calculators. So let's have a look at example 1. It's a bit of a long one, but it says for the equation y equals 4 plus 3x minus x cubed, part A, find the coordinates of the stationary point or points. So to find the stationary points, we do what we did in the previous section, and that's determine the derivative. So dy dx equals, well, that 4 is going to become 0, plus 3x becomes a 3, minus x cubed, so that becomes minus 3x squared. And we know that for a stationary point, I'm just going to write it here, for a stationary point, we will let the derivative, or let dy dx equal 0. And so we're solving 3 minus 3x squared equals 0. Now we've only got x appearing once here, so we can just try to get everything to the other side and solve for x. So we can say this is 3x squared equals 3, x squared equals 1, and therefore x equals, careful with this one because it's x equals plus or minus the square root of 1, so it's plus or minus 1. So they're the x coordinates of the stationary points. To get the y coordinates, we need to sub those x values back in. So when x equals -1, y equals, now of course because we're now trying to determine y, we're going to sub back into the original equation, not the derivative. So y will equal 4 plus 3 times -1 minus -1 cubed, which is 4 minus 3. -1 cubed is -1, so it's take away -1, actually becomes plus 1. So y equals 4 take 3, which is 1, plus 1, so that's 2. Okay, so we've got a coordinate of a stationary point at -1, 2. And the other stationary point was when x equals 1. And to find the y coordinate, we're just going to sub 1 into the original equation. So for y equals 4 plus 3 times 1 minus 1 cubed. So y equals 4 plus 3 minus 1. So y equals 6. Okay, so the coordinates of our two stationary points here are -1, 2 and +1, 6. Now we're going to look at what type of stationary points these are. Okay, so trying to work out, are they minimums, are they maximums, are they points of inflection? And we can set up a kind of table like this, and you don't always have to set up a really neat table. You can kind of do this in a sketch form, but what we're going to identify is, okay, well, let's choose some different values of x and work out what the gradient is at those points of x. So we already saw that when x equals -1 and x equals +1, the gradient, it's written as f dash x here, it probably should be dy dx for this question, but representing the same thing. When x is -1, gradient 0. When x is +1, the gradient 0. So let's pick some numbers on either side of those x values and see what the gradient's doing there. So when x is something less than -1, well, let's just say -2. You want to pick easy numbers to sub in here. So we'll investigate what's going on when x is -2. We also want a number that's a little bit bigger than -1, but smaller than 1. So let's pick 0 because that's going to be really easy to sub in. And number that's bigger than 1 but still pretty easy to sub in, let's just use 2. And so what we're going to try to work out is at each of these values, what's the derivative doing? Is it a positive gradient? Is it a negative gradient? And that'll help us work out the nature of the stationary points. So I don't have a whole lot of space here, so I'll try to do this neatly. When x equals -2, dy dx, which remember is representing the gradient at any point, dy dx will equal, so we've got it written up here, 3 minus 3x squared was our derivative, so 3 minus 3 times -2 squared. So what's that going to be? -2 squared becomes +4, so this is 3 take away 3 times 4, it's 3 take away 12, it's -9. So the gradient when x is -2 is -9. All right, let's go along to the next point. When x equals 0, the gradient dy dx, again it's just 3 minus 3x squared, but it's going to be 3 minus 3 times 0 squared. So the gradient's going to be +3. All right, so when x equals 0, we have a positive gradient. And when x equals 2, last point to sub in. Again, we're subbing into the derivative because we're trying to find out the gradient when x equals 2. Dy dx equals 3 minus 3 times 2 squared, which again is actually 3 take away 12, because that's just going to become 3 times 4, that part. So 3 take away 12, -9. And so when x is 2, the gradient is -9. And so what we've got is, as we go along from left to right, we have a negative gradient, a 0 gradient, a positive gradient, a 0 gradient, and a negative gradient. And even with just those sort of dashes there, and if we drew them a little bit more clearly, I'm just mindful of my space here, but we've got sort of negative gradient, 0 gradient, positive gradient, negative gradient, 0 gradient. That's telling us that this point here where x is -1, which happens sort of here, that must be a local minimum, right? Because we've got a negative gradient before it and a positive gradient afterwards. So the point when x is -1 is a local minimum. So we can say that -1, 2 is a local minimum, or a minimum turning point. I'm going off screen a bit there maybe. That was this point here. And also the point when x is 1, well that's gone, if we look at the left of it, to the left it's a positive gradient, then at x equals 1 it's a 0 gradient, then to the right it's a negative gradient. That's a maximum turning point, right? So that's that point there. So the turning point when x is +1, which is 1, 6, is a maximum turning point. All right, so that's still answering part B. Just didn't have much space to work with there. So we've now identified not only where the stationary points are, but we've used the gradient to determine what type of stationary points they are. And that's obviously going to be helpful for part C when we have to sketch the graph. So if we look carefully at the points we already know, we've got -1, 2. So let's just sort of look at the scale we're working with here. -1, let's say, well, we know the y value's got to go up to at least 6, so I reckon let's go up by 2s. But that's not how it works, is it, Mr. Johnson? 1 and then -2. Negative. I've made a complete meal of that. Why am I counting by 1s when the y-axis is counting by 2s? Sorry about that. This is why you do your graphs in pencil to start with. Okay. So -1, 2. So I reckon along the x-axis here we're going to get away with just going up by 1s. Let's see if I can count by 1s this time. I think I've done an okay job there. So -1, 2, we said was a minimum turning point, and 1, 6 is a maximum turning point. All right. And of course, and we probably should have mentioned this, I should have mentioned this at the start, it always pays to look at what type of function it is, right? This is a negative cubic function, and we've got a good idea about how cubic functions behave, right? When they're negative, they can either kind of come down and just have a point of inflection, or they can sort of go down, then up, then down. So we know a bit about cubics already, and we can use that to piece together and help us understand what we're graphing. There's going to be a y-intercept somewhere in between these 2 points. So let's just say, for the purpose of this example, work out the y-intercept. We're not going to stress too much about the x-intercept for this one. The y-intercept, we're going to let x equal 0. And our original equation was 4 plus 3x, so 3 times 0 minus 0 cubed, which of course is going to be 0. So the y-intercept's just 4. Okay. And our graph will look something like... Again, we're probably going to do this a little bit roughly, but the main focus of the question, I think, was about understanding the nature of the stationary points. We won't lose too much sleep about just how perfect our graph is, which I know is not the right thing to say, but that's how we're treating this one. Okay, but our graph's going to look something like that. Okay, as I said, normally you'd have to find the x-intercept. The reason I'm not doing it in this case is because it's pretty messy cubic to sort of solve. You know, you'd have to factorize and solve if you were trying to find the x-intercept. Usually it'd be a calculator question if you were going to do that. And I don't have my calculator with me to tell you what that x-intercept is. But we certainly have been able to do enough here. And let's label the coordinates we did find. Right, but again, just coming back to what we said at the start, the key idea of this skill, in terms of identifying what type of stationary points you've got, is using the gradient on either side of the stationary point. Okay, so these sort of 3 key ideas will always tell you which sort of stationary point you've got. Particularly, there might be times when you know the graph, so you know what type of stationary point it is already, but you have to justify that it's a minimum or justify that it's a maximum. This technique is obviously a very handy one. So good luck with your questions from 10D, and as always, get in touch with your teacher if you need some help. Cheers.